to this video on how to do nomenclature. Before you even watch this video, if you have not gone through the entirety of the formulas and nomenclature packet and read through all those notes and done the work there, then this video is not for you. This video is meant for you if you've already experienced all the different types of nomenclature and you are ready to practice how to identify what type of nomenclature to use when all these problems are mixed together. If you were to come across any name or formula, what do? This video is for you, but if you haven't done the entire packet yet, go back and do that. That is your first priority. So here we go. If we're given any name of a compound, how are we supposed to identify what its formula is? Well, lucky for you, it's really not that complicated. Just a few things that you need to check for, and then following the steps that you already know how to follow. So we're going to start these first few examples here on the extra mixed formulas and nomenclature practice. Number one, let's do this. So the first thing that I want you to check for whenever you are identifying the formula of a compound, does that compound contain any metals or polyatomic ions? Simple enough. What that's going to do for you, if you find a metal or a polyatomic ion, it tells you that the compound is an ionic compound right away. If you can't find a metal and you can't find a polyatomic ion, then you're dealing with a covalent molecule. And that actually separates the two processes that you would need to follow pretty clearly. So let's do it. Sodium bromide. Well, I can find sodium on the periodic table. I know that sodium is the symbol Na, and I know bromide is, well, we'll get to bromide in a second. Sodium. It's just a sodium ion. Sodium comes from group 1 on the periodic table, so we know that it is going to take on a +1 charge. There's my sodium ion. We also know that sodium is a metal, so this is absolutely an ionic compound, hence why I knew to put a charge of +1 on it as well. Bromide, though, the ending of IDE. Well, if I see the ending IDE, there's a 99% chance that that anion is going to come from the periodic table, which is bromine as an anion, Br would be bromide. If you checked your polyatomic ion sheet for the next 10 years, you're not going to find bromide on it at all, because it is not a polyatomic ion. It is an ion from the periodic table, a monatomic ion, bromide. That's actually a good way to check. If you look on your polyatomic ion sheet, the whole thing, and you can't find that anion there, probably comes from the periodic table. So once we have our cation and our anion with the symbols and their charges, we can just cross those charges down and simplify the ratio if we need to. Lucky for us, a 1-to-1 ratio cannot be simplified. And I say it's 1-to-1 because I bring these numbers down, just the numbers, not their symbols, just 1 and 1. And a 1-to-1 ratio is as simple as it can be. We don't write the ones in our final formula, and thus sodium bromide is just NaBr. Great. Moving right along. Dinitrogen tetroxide. Okay, we got numerical prefixes in this compound as well. That's kind of a giveaway I'll tell you about in just a second. But let's look at the elements. We have nitrogen and oxide. Well, there's no element called oxide, but there is an element called oxygen. And nitrogen and oxygen are both nonmetals. So that means this is not an ionic compound. And we also don't have any polyatomic ions here either. This is a covalent molecule. Dinitrogen tetroxide. Another giveaway, and this is the one that I was talking about, that tells you this is a covalent molecule is the fact that we have numerical prefixes here, di and tetra. That tells you that you're dealing with covalent nomenclature. So what do those prefixes tell us? Well, nitrogen is N. Since it's dinitrogen, di is the prefix we use for 2. Tetroxide, O is oxygen. We do change the ending still in the second element of a covalent molecule, so oxygen becomes oxide. But how many oxides do we have? How many oxygens do we have? Tetra, which is 4. And that's it, N2O4 for our covalent molecule here. Just as a side note, we do not simplify a covalent molecule, right? N2O4 and NO2, these are not the same thing. They are completely different molecules with completely different Lewis structures, so please do not simplify a covalent molecule ever. Moving right along, sodium nitrate. Okay, well, sodium again is a metal, giveaway there, so we know we're going to have a sodium ion, but then we see nitrate. ATE is our ending. There are a few endings and prefixes in nomenclature that tell you you're dealing with a polyatomic ion. ATE or ITE, so ate or ite, those are two suffixes on your anion that's going to tell you it comes from the polyatomic ion sheet. You could also see, like, for instance, perchlorate. Per and ate together, still a polyatomic ion. And then hypochlorite, hypo and ite, still a polyatomic ion. If you see those funky prefixes and suffixes, there's a good chance it's going to come from the polyatomic ion sheet, so make sure that that's handy. Keep that ready. When I check that sheet, I'll see that nitrate is NO3 with a -1 charge. And when I cross those charges down, Na and NO3, make sure you keep your polyatomic ions grouped up together. Bring that down, 1 here and 1 here. Notice I kept that 1 separate from my polyatomic ion. If that number was more than 1, I would have to use parentheses. But since I only have 1 of them, I don't need parentheses. And I also don't even need to write the 1. This 1-to-1 ratio can't be simplified, so I'm just going to put it as NaNO3. No parentheses needed, no 1s needed, done. Next, we have iron 3 oxide. Now, this one's particularly funky. We've got iron 3 oxide. What's that about? Does the 3 tell us how many there are? No. It tells us the charge on the metal. This 3, this Roman numeral 3, is talking about iron's charge. Why? Iron can have multiple different oxidation states or charges. It's always going to be positive because it's a metal, so it's always going to be a cation, but iron could be iron 2, you could have iron 3, and those are the two most common examples of iron, but I'm sure there are others. Iron 3 oxide. What does that do to our formula? Well, we know the symbol for iron is Fe. We know that it has a +3 charge because the Roman numeral tells us. What about oxide, though? The ending is IDE. I don't see oxide on my polyatomic ion sheet, which means it must come from the periodic table. O is oxygen. Since it's in group 6, it's going to take on a -2 charge when it forms an anion. And now we can cross down the charges just like we did with every other ionic compound. Just the numbers. 2 goes down here, and 3 goes down here. Fe2O3 cannot be simplified. That's our final formula for iron 3 oxide. Okay. And that's it. Those are the 4 types of nomenclature. We have binary ionic compounds, so 1 of each element, cation, anion. We have binary covalent molecules, right? 1 element, 1 element. We have ionic compounds that contain polyatomic ions, and then we have ionic compounds that contain metals that are transition metals, or metals that require a Roman numeral to represent their charge. Those are the 4 types of nomenclature that you're dealing with in this class. So as long as you're familiar with how to do those things, the big question is, well, how do I get started? Are there metals or polyatomic ions in the formula? Yes, it's an ionic compound. No, it's a covalent molecule. After that, you just have to follow the same strategic procedures that are found in the formulas and nomenclature packet, which again, if you haven't done that yet, please make sure you do. And stay tuned for the next video where we're going to go how to go from a formula to a name. See you there.